So in this section, we're going to look at properties of functions. We're going to look at what it means to be an even function or an odd function. Sometimes they're neither even or odd. We're going to look at finding where the graph is increasing, decreasing, constant, where we have local max, local mins. And that is what we're covering in this section. So definition. You need to know what it means for a function to be an even function. So we say that a function f is even for every x in the domain the number negative x is also in the domain. And the following has to hold. And f of x is the same thing as f of negative x. Well, let's just talk about that for a second. So that's saying if we have some value x, let's say on the graph here, it's saying that that x value, negative x, also has to be on the graph, and it has to be the same y value. And so notice any value that we plot over here is going to be a mirror image across this y-axis. So even functions are symmetrical. Across the y-axis. And we were testing for symmetry before. So we saw that if we could plug in negative x wherever we saw an x in our function, and we got back our original function, that this was symmetrical across the y-axis. A function is said to be odd so our function f is odd if for every x in the domain the number negative x is also in the domain. And the following has to hold. So in this case, if we plug in negative x wherever we see an x, we should get back the negative y value of the original x, so negative f of x. Odd functions. These are symmetrical across the origin. Okay, so we can test to see if a function is even or odd. If none of those conditions hold for either being even or not holding to be odd, then we would say it's neither even or odd. So let's pull up an example. So in this example, we have h of x equals x all over x squared minus 1, and the directions ask us to determine if h of x, this function, is even, odd, or neither. If we go back up to the definition, notice that in each definition, we have to look at what f of negative x is. So I normally test first for it being even. So if I want to look at seeing if this is an even function, let's first look at what is h of negative x. And if it's even, then this would equal our original function h of x. So h of negative x, that's just telling me that I'm going into my function, and wherever I see an x value, we're going to replace it with negative x. So we have negative x here all over. I see an x, I'm going to have to square it. So negative x quantity squared minus 1. If I reduce this down, I get negative x. Well, negative x times negative x, that negative x quantity squared gives us back positive x squared minus 1. So looking at this, h of negative x is not the same as h of x. So I can say that this is not even. So mathematically, you can say the word therefore with those 3 dots that kind of make that triangle. So to test to see if it's odd, we want to see, does h of negative x, which we already found, is this equal to negative of h of x? Well, let's first look at negative h of x, because we already found that what h of negative x is. H of negative x we found to be this. So looking at negative h of x, that's just telling me I'm taking my function h of x and multiplying that by negative 1. So this is negative of this x all over x squared minus 1. Well, I can move that negative up into the numerator if I want. And so this is the same thing as negative x all over x squared minus 1, which notice is the same thing as this over here that we got, which is the same thing as h of negative x. So is it odd? Yes. So pretty much you were doing this before when you were testing for symmetry. So I threw up 2 theorems or a theorem in here. So, and we had already stated this, but it says graphs of even and odd functions. A function is even if and only if the graph is symmetrical to the respect of the y-axis. And the function is odd if and only if the graph is symmetrical to the respect to the origin. So let's look at what it means by definition, mathematically, to be an increasing function, a decreasing function, or a constant function. We say a function is increasing on an interval I if for every choice of x of 1 and x of 2 in I, x of 1 is smaller than x of 2, then f of x of 1 has to be smaller than f of x of 2. Okay, let's look at a picture of that and what that's saying. So it's saying we have 2 x values. So let's say right here, x of 1 and x of 2. It told me that the one x of 1 had to be smaller than x of 2. So my x value, x of 1 is smaller than x of 2. It's saying then my y value at x of 1, so let's say that this is my y value. means I have a point right here, has to be smaller than my y value when x at x sub 2. And that has to be the case for a function is increasing on I if for any x sub 1 or x sub 2 that you choose on that interval. And so it would be going up. So at least from there, and then it's even increasing more than that on how I drew that, but it's increasing from the x sub 1 to x sub 2. We say that it's decreasing. Same conditions hold, except that the y value is going to be bigger for the first x value. I'm sorry, yeah, than the second. Then the y value of the second point. So if this was x sub 1, has to be smaller than x sub 2. The y value, though, f of x sub 1, has to be bigger than the y value, f of x sub 2. So it'd be decreasing there. And the last one, we can see if it's constant. So a function is said to be constant on an interval of I. If you choose an x in I, the values of f of x are the same. So this is telling me I have a horizontal line. So if I have some x sub 1 here, some x sub 2 here, or any value in between, f of x sub 1 is the same as f of x sub 2. It's a horizontal line. So notice, I always look at graphs though, because we're going to be looking at graphs. When is it increasing? Where is it decreasing? Max and mins. Once you get further, when you get into calculus, you'll get tools to do that algebraically. But we'll be looking at graphs. And I just kind of think of it, if I am looking at the graph and I am moving left to right, reading the graph left to right, am I going to be walking uphill or downhill? If I'm walking uphill, I'm increasing. And so this is increasing, where this is a function where I'm decreasing, going left to right, right? I'd be going downhill. And then constant, I'm on level ground. I'm just moving straight ahead on level ground, not rising or falling. So looking at the function or the graph of the function, the first thing we want to know is part A. Let's look at maybe the domain. So looking at this, I notice that I have endpoints because I have solid points, and this doesn't have an arrow shooting downwards. If it did, then it would be going on in that direction forever. And so domain are all the x values that we're hitting in this graph. And so we're looking at the x value here is at -3. And the x value here is at +3. And so I'm looking at all the x values in between -3 and, I'm sorry, I said, yeah. That is x equals -3, sorry. Is -3 to 3. Another way to write that, -3, just to reunify that these are x values. -3 is less than or equal to x is less than or equal to +3. The range, these are all the y values that we're hitting on the graph. And so if I look at the smallest y value, notice the smallest y value in here is -2. And I'm including it because that's a solid circle. So -2 all the way up to the highest y value that I'm hitting is 2. So notice I hit all the y values in between. If there had been a jump in the graph, there might be some y values that we don't hit, and we would have to take that in consideration. but we have all y values between -2 and 2. Another way to write this is -2 is less than or equal to y is less than or equal to 2. So now we want to look at where is this increasing, decreasing, and constant. When we're looking at interval notation, we're always looking at our x values except for range. And so if I'm looking at where is this increasing, I'm looking at all the x values where this is increasing. And so thinking of it moving left to right, I'm going up here, left to right. So we want to look at the x value where it's starting. That x value, though, that it starts at is -3. And notice that once I get to x equals -2, I've stopped going up. And so we're increasing. I'm going to put a bracket at this -3 just because it's a point and we're starting there. But when I get to -2, it becomes constant. And so we're just going to put a parentheses there. Union. So if it's a place where it's changing direction then just put a parentheses on that piece. And so notice right here at x equals 0, I'm starting to go back up. So I want to look at until what x value. At this x value of 2, I stop going up and I start going down. And so all the x values where it's increasing, we have from -3 to -2, union from 0 to 2. If we look at where is it decreasing, where is it going down left to right? And so there's only one spot in here that I see that the graph heads downwards. And so again, I'm looking at the x values, and that x value, it starts going down is at 2. So parentheses 2, comma, and where is it stopping? And it stops and doesn't change direction there. So at 3, I'm going to put a bracket because that's a solid circle. And then constant. This is where it's horizontal. The graph is horizontal. The graph is horizontal in this piece. And so looking at the x values where it's horizontal, we're starting at x equals -2 and stopping when x is 0. So parentheses -2, 0, parentheses. The other question in this was looking at the graph. Is the function even, odd, or neither? If it's even, this would be a reflection across this y-axis. And I notice if I folded my paper along this y-axis, I wouldn't have a mirror image. And so this is no. We talked about it being odd. It would be symmetrical across this origin. So if I folded my paper across the x-axis and the y-axis in terms of fourth and the fourth, would it be a mirror image? And I notice it's not going to. So this is neither even or odd. Okay, so let's stop there and then we'll come back after a little break.